Record on cloud. Oh, okay. Every time you tap, and then let me just do like hide video and hide also naming annotations. Oh God, come on. Hide everything. No, this is gonna stay here. I don't know why. Usually you can remove it, but oh. I'll just put it. Is this okay leaving it there? I mean, it's I know it's a bit annoying, but apparently there's no. Okay, so let's do this. I'm going in the right way or not?
Yeah.
So okay, fine. So hello everybody. I'm Andrea Sacchi, and along with Caroline, we are the new members of the head seminars organizing committee. Today, the speaker is Antoine. He is a final year statistics PhD student at the Imperial College of London, working with Professor David Van Dyke on Bayesian methods of applied to astrophysics. So the field is yours.
Thank you very much. By the way, I don't know if this works or not, but I guess I don't need it. Thank you. Test. All right. So yeah, thank you very much for the invitation. So I'm happy to present this project I've been working on during my PhD that's been recently accepted for publication. So I've been working with my supervisor and Aneta here at the CFA and TAC at Penn State. So we designed this Bayesian method to look at gravitational lens time delays using a type of time series processes called CARMA processes to model the age and light curves. So I assume, or I imagine most people are familiar with the gravitational lensing phenomenon, but I'll just give a quick introduction. So the idea is that you have a quasar or a galaxy, something that's very bright that emits light towards Earth, and if there is another galaxy in the middle that has a gravitational field that's strong enough, the light rays will be bent on their way to Earth, so that different rays will travel different distances on different paths, which means that they will arrive on Earth at different times. So you observe, instead of a single light curve, you observe multiple copies of the original light curve that are delayed in time. So the brightness fluctuations that you might observe in a light curve will occur at different times in the different copies. And I guess the physics motivation to look at this problem is that if you can somehow measure or estimate the time delay, which is the difference in arrival times of those images, or the difference in times at which the same fluctuations occur in different copies, you can use that to constrain important cosmological parameters, such as the Hubble constant. So I'm a statistician, so I'm interested in this problem because it's a challenging data analysis problem, namely because the data is subject to a lot of irregularities. So due to observational patterns, you have irregular sampling, so you wouldn't have, a measurement at regular sampling times. You also have big gaps in the data due to celestial cycles. So as you can see here, which further complicates the analysis. And also in the light curves themselves, you have multiple sources of fluctuations. So you have the strong lensing effect, which is what causes the shift in the x-axis, the time delay. But you also have other effects which cause brightness magnifications, and also microlensing events, which is, I think, what happens when the actual different light rays travel through the lensing galaxy. This can impact the long-term trend in the light curve, which is important to take into account in the modeling approach. And also the data is subject to measurement errors that are also heteroscedastic, which means they have a different variance at different observation times. So to put it simply, we get, in a very simple setting, in a doubly lensed setting, you get two light curves, and the goal is to estimate the shift in the x-axis, which is the time delay. So here is a bit of a review of what people typically do to tackle this problem. You have two families of method. One is more, I guess, data-driven and non-parametric, where you can imagine shifting the two light curves on a grid of points and then measuring some kind of distance between the two light curves. And, whichever shift is going to give you, is going to say that the light curves are aligned the most, would be a likely value for your time delay. And then typically you can produce uncertainty estimates using Monte Carlo simulations, or repeating that same process over and over again with simulated data sets. But that's quite computationally expensive. And the other, I guess, big class of methods is a more, I guess, statistical approach, where you're actually going to try to model the stochastic variability in the light curves that you observe. So that can be integrated in a lot of different modeling settings, but I'm a Bayesian guy, so within the Bayesian setting, we always like to say that it's more principled, I guess, and you get so Bayesian stats, you derive posterior distribution on your parameters of interest, so you have more direct quantification of the uncertainty in the time delay parameter, which is that x-axis shift. A few years ago, there was a challenge that was created to encourage research in the area, and so a lot of different teams proposed time delay estimation techniques, and the collaboration that came out on top is COSMOGRAIL at the EPFL in Switzerland, who basically use a combination of different techniques, more in the first family of methods, to produce their estimate. And my collaborator, TAC at Penn State, also did very well and proposed a Bayesian method in which he modeled the variability in the light curves using a damped random walk process, or OEU process in the stats literature. And this is what my project is about, trying to take this method and see how I can improve it a little bit. So before I can actually tell you what we did, I guess I need to introduce roughly what the method does. So basically, you make assumptions on how the different lensing effects, so the strong lensing and micro lensing affects the light curves, and conditioning on those assumptions, make parametric assumptions. You can kind of reconstruct an intrinsic light curve, which will be what did the light curve look like before it was lensed by the lensing galaxy, and you construct it from the two lensed counterparts. And once you construct this intrinsic light curve, in that research paper in 2017, they modeled it with a damped random walk process, and then you can perform Bayesian inference to sample from the joint distribution of both the light curve parameters and the time delay parameter, and then you can construct from Monte Carlo draws the posterior distribution of the time delay parameter. What we did is propose two developments of this method in items 2 and 3. So instead of modeling the light curve with a damped random walk process, we extended that to the more general flexible class of CARMA process, which stands for continuous autoregressive and moving average process. And we also proposed a computational development, updating the inference algorithm from MCMC to nested sampling. And I'm going to explain in a second why we made those choices. So there were very specific, I guess, not issues, but limitations to the current approach that we try to tackle. So dam random walk process in the astrophysics literature was, I guess, the go-to for a long time. And then people started looking at more general classes of processes. So CARMA processes are actually a mathematical generalization of the dam random walk. And there was a realization that with a more flexible process, you can model a wider range of observation. And because the dam random walk process only has 2 free parameters, whereas the current process, depending on its complexity, can be a lot more flexible. So because of this success in modeling age and light curves with those CARMA processes, there was a big motivation for us to integrate that into the time delay method. And so there's one reason is that we want to be able to analyze more observations. And also, if you have a more flexible model, hopefully you can have a better fit to the data, which can improve the accuracy of the time delay estimate. So replacing dam random walk with CARMA processes. And on the computational side, there is actually a lot of computational issues with those time delay estimation methods. And also on the CARMA modeling side. So CARMA parameters and time delay parameters are both quite multimodal in their posterior distributions, and multimodal distributions are notoriously hard to sample from using typical methods like MCMC, although there is some more advanced algorithms that are developed to tackle it. But one of those algorithms is nested sampling, in particular the multi-nest iteration, which is quite useful to model multimodal, sample from multimodal distributions. One feature of most time delay methods also usually is that you kind of need to input an initial guess of what your time delay is, which is limiting in the sense that you need to come up with a good idea, and sometimes so you need actually another method to come up with an initial guess. And for example, TAC in 2017 with the dam random walk method computed a very expensive profile likelihood. So I'm not going to go into the details of what it actually is, but it's a very computationally heavy way of mapping the likelihood function and trying to find if there are modes and plausible initial values for the actually main algorithm, which is a bit of a burden in my opinion. And what our computational development allows as well is to perform model selection. So multi-nest or nested sampling methods at the origin are designed to evaluate the Bayesian evidence, which is a marginal likelihood of the data, so your denominator in Bayes rule, and multi-nest allows to do that at no extra computational cost on top of the posterior sampling. And it's quite useful because when you're working with CARMA PQ process, you're faced with a model selection problem of selecting the hyperparameters P and Q, which is the autoregressive and moving average order of your process. I'm just checking my time. So this is what the data looks like. So we're getting observation times and magnitude, brightness measurements for the 2 light curves, as well as measurement errors for each of those. And so this is how we make modeling assumptions. So we're saying that our brightness measurements for both light curves actually are realizations of an unobserved continuous light curve, and that one of them is a time and magnitude shifted version of the other, and those shifts occur because of the lensing phenomenon. So the strong lensing effect causes a time shift, which we model as in equation 1, just we have a time delay parameter delta. There is also a magnitude effect, so we add a magnitude constant, and in case where we observe a microlensing event, there is an extrinsic long-term variability that you observe in the light curve, which we model in this case with the polynomial regression that we can make of degree m, that we can make as flexible as we need, and it's been one of the ways that micro lensing can be modeled in the literature. So we continue with that. So this is our main model, and then what we do with that is we reconstruct the intrinsic light curve, as I said. So As you can see on this picture, we want to take both lens counterparts and then adjust for those effects to construct an intrinsic light curve and then model it with our time delay process. So this is how we construct the light curve. It's just the math for it, but the idea is you correct for the time shift and correct for the microlensing and put them together. So we've constructed this intrinsic light curve, and then what we now want to do is model it with our time series process. So again, we're extending from the simple damp random walk process, which is a CARMA 1.0, to a CARMA PQ process for the reasons I explained earlier. Here, I just give a bit of an introduction on those processes. We don't need to look into the math exactly, but you have a lot more free parameters with the CARMA process. It's a much more flexible process. So you're hoping to model a wider range of observation and closer to the data, and to give a bit of a more physics, I guess, driven argument. If you look at the autocorrelations, damn random walk model only allows for a single exponentially decaying autocorrelation, whereas you can have something substantially more complex with the CARMA process. You can have exponentially decaying autocorrelations, but also sinusoidal functions, sinusoidal components in your autocorrelation function. And so that's in the time space. If you prefer to think in frequency space, looking at the power spectral density, the CARMA process also can have multiple breaks and actually account for frequencies in the power spectral density, which is not allowed by the damn random walk. So all those processes, CARMA and DRW, are Gaussian processes. Typically, a Gaussian process likelihood is quite expensive to evaluate. You have to invert an n-by-n covariance matrix, which scales cubically with the number of data points. Thankfully, the CARMA processes have a special structure that you can leverage to actually compute the likelihood in linear time, which makes them actually quite scalable to large data sets. So depending on, you have different options. You can use a camel filter algorithm if you represent your CARMA process in a state space, or Mr. Foreman Mackey in 2017 came up with an algorithm to actually also invert the covariance matrix in linear time as well. We found in practice that the GP representation is much faster than the Camel filter algorithm, although they have the same complexity. So we operate under the Bayesian paradigm. So I guess this isn't news to anyone, but so we're trying to derive the posterior distribution of our model parameters given the observed data, and we formulate we usually use uniform priors on all of our parameters and with specific boundaries to make them proper. And so, yeah, so we're using nested sampling to produce a sample from the posterior distribution. This is just a recap from what I already said. There's a lot of benefits from using it, at least in my opinion, which was the motivation to extend the computation. So it allows us to tackle the multimodality and also the model selection problem, selecting the hyperparameters. So the complexity of your microlensing model, and then the complexity of your time series model with the P and Q parameters of the CARMA process. So we ran a simulation study. I don't have time to go into the details right now, but we made sure that the model was working statistically, and we compared kind of with the performance metrics that were suggested in the literature, the performance of our model. I guess it's unfair because I did it 7 years after the time delay challenge, but we were within the benchmark, and also we managed to show in the simulation study that CARMA processes are almost always selected as the better model compared to the damn random walk model. And then we actually studied actual observations that we also that was studied by other time delay method teams in the literature, so we could compare our estimates. Of course, the truth is not known, but that's what the simulation study is about, making sure that it works, hopefully. So we looked at those 6 quasars, and I'm gonna dig a bit into 2 of them, but so here's an illustration of kind of how the method works. We, again, putting light curves together and modeling the intrinsic, and then we managed to have a bit tighter error bounds. Our estimates still kind of consistent with the value that other people find. And the reason why we looked at this observation in the first place is the damn random walk based method produced a highly multimodal distribution for time delay parameter that covered a lot of ground, but not that value that was found by other people. So didn't work that well. And it's another example. And here I give an example about how if there is, for example, reasons to believe that there might be a frequency component in your light curve, well, the CARMA process allows you to leverage that to reduce the uncertainty, because your time delay can only be, a multiple of some specific value. But then you have to make sure that you actually believe that there's a frequency. But so it was kind of more of a two example. I think I'm running out of time. I passed the 20 minutes, so I should conclude. But here's just results are our estimates compared to others in the literature. And also what I thought was quite cool is we also managed to produce an estimate for this quasar 1349 that some other people weren't able to, and it was, I guess, consistent with a very vague prediction on the order of someone said that it should be of the order of a year, which we kind of have, that's in days. So I thought that was nice. But and then just a few pointers of potential extensions. Look at multi-band light curve that's being done with the damn random walk process, but is yet to be done with the CARMA-based method. And then obviously now that we produced estimates of the time delay, it would be nice to see what happens when we use that to produce estimates of those cosmological parameters that we're trying to constrain in the first place. And maybe look at time delays that are arising in other settings than gravitational lensing. But yeah, thank you very much.
Questions?
So you tested it for multiple P and Q of the CARMA process. Do you have a method to pick one of them? Do you have a market selection process? Yeah, so usually we just, for every model that we fit, our algorithm outputs the Bayesian evidence. So marginal, so how good the model fits to the data. So usually we just pick the highest evidence model. Or there's another thing that we can do, because it might be the case that you have several models that are quite high evidence, so you can actually combine them if you want, using Bayesian model averaging. But we're lucky that either one model dominated the model space, so we picked this one, or the few models that had similar probability were also having similar posterior distributions, so that in a couple of the setup figures that you had, some of the PQ versions were inconsistent, I think, with each other, with that one.
The other one, you mean?
You had that one, yes.
Yeah.
So, for example, the upper right, they're giving different answers, different modes. So, which one would you recommend us?
Yeah. So what I did in this plot is I applied CARMA 213, which I thought was kind of I use it as a baseline because it's the simplest CARMA process. It's CARMA 2.1 because otherwise just a color process, or if it's 1.0, it's a damn random walk. and third order micro lensing just to be on the safe side if something happens. But it's just a baseline, and then the blue one is the highest evidence model. So it's just to show that some like the baseline model won't necessarily work because in case where you have more complexity in the light curve or in the micro lensing. But yeah, it's just an illustration.
Any other questions?
No, this just trying to make this relate this to what I understand about lenses. So, I mean, lenses are really images, right? And in this case, you've got a single AGN, which is a lot brighter than the things around it. So quasars really are galaxies, but they have a central brightness that's much brighter than everything else, and it's also the only time variable part because it's the only bright small bit, right? So you've got two points in a lensed image. Now, lensed images are actually very difficult to compute if you have more than just 2 points, because the lenses themselves are really complicated. I mean, they are more complicated than you can possibly model or constrain with the data at hand, because the lens is a whole galaxy. It may be roughly spheroidal, but you can't supply it with enough parameters to really match a true lensed image of a complicated thing. And so I'm wondering, once you get this number, this one delay in 210 days or whatever, how does that relate to cosmology if you're not at all sure of what the lens is like?
Yes, I guess the astro part is not my strong suit nor my field of expertise, so I'm not really sure, to be honest. My job stops, I guess, when I produce the number, and I just do the stats. Maybe Anita will be better suited to.
Well, it's a good question. I mean, we kind of thought about looking back at the lens, because what Antoine used when the light goes into all of the generated the images and the database. But going back to the lens, it's complicated. So we can done and do any inversion cosmology that's just looking at manipulated images.
Well, how much do you use the current best model of cosmology in your Bayesian priors?
We don't use any physics induced priors.
No physics.
Yeah. It's just uniform distributions on a plausible range.
You could probably use some physics and make it a lot faster computation.
Yeah, sure.
Yeah.
I guess, yeah.
So I can see no questions from the chat. Upstairs, no. So, another one.
When you said that there was some competition and there was winners, what do you mean by winners? Is this speed or accuracy? How?
It was using those performance metrics that were used in the time delay challenge, and whichever scored the best in terms of those metrics. So you're trying to minimize them.
Just to follow up on that, the winner was determined by how many of the data set the sample dose were actually worked on.
Yeah.
And TAC actually started this, we had very little time, so we didn't actually complete all of them. So that's we only looked at the hardest part.
You guys would disqualify?
No, we were almost disqualified, but we made it snuck in through it. So that's
Yeah.
why it wasn't the
Yeah, it's basically those metrics multiplied by the fraction of data sets that you're trying.
Going back to Tony's question, I think that you guys are already assuming a single delay in your model, right?
Yeah.
Regardless of what kind of structure and add. But when you describe one of the with the micro lending, it
Mhm.
appears to me, at least maybe you are doing this for the presentation, but it appears to me you are assuming lending for the one part of the source, not the other. What if both of them has a lending, micro lending effect, then how do you deal with it? Do you sort of push everything into the one side and then to the
Yeah, you can do that, or have a micro lensing component for both. Yeah, absolutely.
Okay, so if you have further questions or comments, you can reach him.
Absolutely.
You have filled your Google spreadsheet with your free time.
I can make one. You can make one. Yeah,
Oh.
so Antoine stays here to Friday. Right?
Yeah,
Okay.
yeah. Sounds good.
Let's take our speaker.
Thank you. Here.
Yeah.
Is a switch here.